Okay, well here's an even more complicated circuit. We've got one power supply and 1, 2, 3, 4, 5, 6 resistors. How can we deal with this? Well, if we think about this for a while, you might notice, well, that 4, 5, and 6 ohm resistor, what are those? They are all in series. So we can replace the 4, 5, and 6 ohm with a single resistor that's equal to the sum of those. So what would that be? Well, 4 plus 5 plus 6 is 15. So we'll replace that with a single resistor of 15 ohms. Okay, well there we go. There is a new circuit where we've still got the 1, 2, and 3 ohm resistor, but we've replaced the 4, 5, and 6 with a single resistance of 15 ohms. Well, now what? Well, now we might notice that 15 is now in parallel with the 2 ohm. So we can replace that with a single resistor using the equivalent resistance for resistors in parallel. Well, you figure it out, see what you get. 1 over 15 plus 1 over 2, add those up, take the inverse. What I think you should get is 1.76. So 1.76 ohms. We'll replace those two with a single resistor of resistance 1.76 ohms. Okay, well there we go. There is a new circuit where we've replaced the two resistors in parallel with a single resistor of resistance 1.76 ohms. And now what? Well, now we might notice the 1.76, and the 3 ohm resistor are all in series. So we can replace all three of those with a single resistor of resistance equal to the sum 1 plus 1.76 plus 3, which is what? 5.76. So let's replace all of those with a single resistor, 5.76 ohms. So there we go. We've got now a very simple circuit with one power supply, one resistor with a resistance 5.76 ohms. What is the current now leaving the battery? What current I? Well, now we've only got one current through this entire circuit. We know V equals RI. In other words, I is equal to V over R, 12 volts divided by 5.76 ohms. Well, what's that? It turns out that is 2.08 amps. There we go. So what we have is that the current leaving the battery is 2.08 amps. But that must be the same current as is leaving the battery over here, as is leaving the battery over here, as is leaving the battery over here. So we know that in this complicated circuit, the current leaving the battery must be 2.08 amps. That must be the current going into the battery, 2.08 amps. That must be the current going through the 1 ohm resistor, 2.08 amps. That must be the current coming down through the 3 ohm resistor, 2.08 amps. But we don't know when that current comes up here, we don't know how that current divides. How much goes through the 2 ohm and then how much goes up through the top through the 4, 5, and 6. Well, let's see if we can calculate how much current actually goes through the 2 ohm resistor. We'll call that I sub 2. Now, we're going to use Kirchhoff's loop rule, and we're going to go around this loop. We don't need any of that anymore. I'm just going to erase that, and we'll apply the loop rule. Okay, let's start here, and let's go around the loop. We're going to go around just this lower loop here. Starting here, we jump across the power supply. That's 12 volts. We jump across the 1 ohm. Now, notice, we know that the current in the 1 ohm is 2.08 amps. So, Ri, we're going to have minus 1 ohm times 2.08 amps. Then we jump across the 2 ohm resistor with a current of I2. We're going with the current, so again that's going to be a decrease, minus 2 ohms times I2. Then we jump across the 3 ohm resistor. We know again that the current in the 3 ohm is 2.08 amps. So we'll have minus 3 ohms times 2.08 amps. And that brings us back to where we started. All of this must equal 0. There we go. Now, the only thing in that equation we don't know is I2. So we can solve that for I2. We have 12 volts, minus 1 times 2.08, so that's minus 2.08 ohms times amps, that's a volt. Let's come over here, minus 3 ohms times 2.08. 3 times 2.08 is what? 6.24. Minus 6.24 ohms times amps, volts, minus 2 ohms times I2, and all of that must equal 0. Okay, so what do we have? We've got 12 minus 2.08 minus 6.24, that is 3.68. 3.68 volts equals, let's bring this over there, divide by 2 ohms, and we have I2 is equal to 3.68 volts divided by 2 ohms, which leaves us with I2 is equal to 1.84 amps. The current through the 2 ohm resistor is 1.84 amps. There we go. Now, we could actually apply the loop rule around the outer loop if we wanted and solve for the current up here, or we can do something a lot simpler. We can apply the branch rule at this point right here. What current do we have going into that point? Well, we have 2.08 amps going into that point. What do we have coming out of that? Well, we have 1.84 amps, and whatever this current is here, we'll call this I1. I1 is going to be the same current that goes up through the 4, across through the 5, and down through the 6. So we've got I1 plus I2, in other words, I1 plus 1.84 amps coming out of that point, equals I1 plus 1.84 amps coming out of that, subtract the 1.84, and what do we get? We get I1 is equal to 0.24 amps. And there we go. We've got all of the currents through each, we've got the current through each resistor. And we could write that in. The current through the 4 amp is 0.24 amps. The current through the 5 ohm is 0.24 amps. The current through the 6 ohm, 0.24 amps. So we could actually put all those currents in there with their directions to indicate exactly how much current is going through the resistors in the entire circuit. Very, very good. Well, now this circuit, while it started out looking complicated, was really just a combination of things in series and parallel. Can we do anything that's even more complicated? Something that might not be able to that we might not be able to just reduce using series and parallel right off the bat. Well, let's take a look at something even more complicated. Okay, here's something that looks even more complicated that's got 2 power supplies. How are we going to deal with this if there are 2 power supplies? Well, let's put in some currents. Even though we don't know what the values of what they are, let's see if we can kind of guess what the directions might be. We would expect, this is the high side of the 14 volt power supply, we would expect the current to come out of that side. Let's call that one I1. Here's a 10 volt power supply. We would expect the current to come out of this side, so let's say here's a current coming out here, we'll call this one I2. Now what's going to happen? We've got current coming out this way, coming down here. What's going to happen at this junction? We would expect those currents to maybe go this way through the 2 ohm resistor. So we've got some current here, we'll call that maybe I3. All right, well there we go. We've defined the currents. Let's apply Kirchhoff's rules. Let's apply the branch rule first. So at this point, what currents do we have going into that point? Well, we have I1 and I2, so we have I1 plus I2. And what currents do we have coming out of that point? We have current I3 coming out, so this must equal I3. So I1 plus I2 equals I3. Now, let's apply the loop rule, and let's apply the loop rule around this lower loop here. Let's start down here. Oh, sorry, you could apply the branch rule again at this point, but what would you get? You'd get I3 equals I1 plus I2. Again, no new information. So let's apply the loop rule starting at that point. We'll come across here, jump across the battery, and what do we get? We get 10 volts. And then come up to the 2 ohm, jump across here. Notice again we're going with the current I3, so that's going to be a voltage decrease. So we get minus 2 ohms I3. And that brings us back to where we started. That equals 0. There we go. Now let's apply the loop rule for the upper loop. We'll start up here, come across here, jump across the 14 volt, and what do we have? We have 14 volts. And then jump across the 10 ohm. Again, we're going with the current, so that's going to be minus 10 ohms times I1. Then come down here, again, jump across the 2 ohm. We have minus 2 ohms I3, minus 2 ohms I3, and back up to where we started, equals 0. There we go. Well, here we've got 3 equations with 3 unknowns, the unknowns being the currents, I1, I2, and I3. So how are we going to solve this combination of equations for the unknowns? Well, in this case, it's pretty straightforward. We can actually solve this one. This equation, we notice, only depends on I3. So we can solve for this one. Bring the 2 ohm I3 over here, divided by 2 ohms, and what do we get? We get I3 equals 10 volts divided by 2 ohms, 5 amps. So there's I3. We know I3. Well, notice this equation only depends on I1 and I3. We can take our solution for I3 and put it in here. Then this equation would only depend on I1. Something I've mentioned before. If you want to use an equation to solve for something, that equation has to have what you want to solve for it in the equation, obviously. But you have to know everything else in that equation. If there are 2 unknowns in an equation, you can't solve it for that unknown completely. You can only solve it for an unknown then in terms of the other unknown. Well, here, now that we know I3, we can use this equation to solve for I1. So what do we get? We get 14 volts minus 10 ohms I1, I1, minus 2 ohms times I3. Now I3 is 5 amps, so 2 ohms times 5 amps, that's 10 volts. So minus 10 volts, and that equals 0. So what do we have? We've got 14 volts minus 10 volts, that is 4 volts, equals 10 ohms times I1, divide by 10 ohms, and what do we get? We get I1 equals 0.40 amps. There we go. We've got I1. I1 is 0.4 amps. Then come up here. Now we know I1 and I3. We can use that to solve for I2. I2 will be I3 minus I1. In other words, 5 amps minus 0.4 amps. What do we get? I2 will be 4.60 amps. There we go. So even when we have a circuit that's not just series and parallel, we can always go back to Kirchhoff's rules and apply them and solve for the unknowns in that case. Now, that's not going to work in every single possible circuit, but for the circuits that we'll have to deal with, it will. Excellent. What we're going to do next time is that finishes the material for our first exam. Next time, we're going to start working on a completely new unit, magnetic fields, a new force and a new field. Okay, see you next time.